Have you ever pondered the possibility of using black holes as energy sources? It sounds like a plot from a sci-fi movie, right? Well, black holes, the most potent objects in the universe, hold a power so immense that the human mind struggles to comprehend it. Their gravitational pull is so strong that nothing, absolutely nothing, can escape their grasp. This brings us to an intriguing question. Could we, the ambitious species that we are, ever harness the gargantuan power of black holes as a source of energy? A recent theoretical study suggests that we might indeed be able to do so. Black holes are not merely cosmic vacuums. They are intricate celestial bodies with unique properties that, if understood and manipulated correctly, could potentially serve as the ultimate power source. The study proposes two ways to use black holes as energy sources someday, tapping into their rotational and gravitational properties. Interestingly, the lead author of the study, Zhan-Feng, a postdoctoral researcher at the Kavli Institute for Astronomy and Astrophysics at Peking University, likens black holes to batteries. He explains, "We know that we can extract energies from black holes, and we also know that we can inject energy into them, which almost sounds like a battery." In the first hypothetical scenario, scientists could charge the black hole by injecting it with massive electrically charged particles. Once the black hole itself develops an electric field that begins repelling any additional charges, it would be considered fully charged. The available energy would then come from a combination of the electrical charges injected into it and the mass of those electrical charges. The researchers even calculated the efficiency of this recharging process to be around 25%, which is staggering, to say the least. So let's dive into the two methods that scientists propose for extracting energy from these astronomical powerhouses. Yes, we are talking about turning black holes into cosmic batteries. It might sound like a wild idea, but remember, the reality of today was the wild idea of yesterday. Firstly, imagine charging a black hole, much like you would charge a battery. An intriguing concept, isn't it? Well, this involves injecting the black hole with massive electrically charged particles. Now, the gravitational pull of a black hole is immense, so these charged particles will continue to be sucked in, feeding the black hole with energy. This process continues until something fascinating happens. The black hole starts to develop its own electric field that begins repelling any additional charges. Imagine a battery so full that it starts to push back. It's a bit like that. This electromagnetic repulsion eventually becomes greater than the gravitational pull of the black hole. At this point, scientists would consider the black hole as fully charged. But where does the available energy come from? Here's where Einstein's theory of general relativity comes into play. According to this theory, mass can be treated as equivalent to energy. This means the black hole's available energy would come from a combination of the electrical charges injected into it, as well as the mass of those electrical charges. So, in essence, we're not just charging the black hole with electrical energy, but we're also transforming the particle's mass into charge energy. It's like a 2-for-1 deal in the world of theoretical physics, and it underscores the incredible potential of black holes as a source of power. The beauty of this process lies in its simplicity. We're essentially using the same principles that govern our everyday batteries. It's just that, instead of charging a small device that fits in your pocket, we are charging one of the most powerful objects in the universe. But of course, this is all theoretical. We're still a long way from actually implementing these ideas. Still, it's fascinating to think about the possibilities. In essence, we'd be transforming the particle's mass into charge energy. And who knows, in the future, we might be able to harness the mind-blowing power of black holes, turning them into the ultimate energy source. Now, let's talk about efficiency. How efficient would a black hole battery be? The answer to this question might surprise you more than you'd expect. The researchers who proposed this concept have crunched the numbers and came up with an astounding figure. They've calculated that the efficiency of the recharging process would be about 25%. At first glance, 25% might not seem like a lot. However, let's put that into perspective. This percentage means that a black hole battery could transform about a quarter of the mass inputted into available energy in the form of an electric field. Now, this is where things get truly mind-boggling. With this level of efficiency, a black hole battery would be about 250 times more efficient than an atomic bomb. Yes, you heard that right. 250 times. This is an incredible leap in power conversion, one that could potentially revolutionize our understanding of energy sources and their applications. This efficiency arises from the unique properties of black holes. Remember, according to Einstein's theory of general relativity, mass can be treated as equivalent to energy. Hence, the black hole's available energy comes from a combination of the electrical charges injected into it, as well as the mass of those electrical charges. As the lead researcher Zhan-Feng succinctly put it, the black hole battery is transforming the energy of the particle's mass into charge energy. So we're dealing with a power source that can convert a significant portion of mass into energy, a feat that is currently unparalleled by any known energy generation method. This is the kind of energy efficiency that could power future space missions, sustain advanced technology, and potentially even provide a solution to the world's ever-growing energy needs. So, we've successfully charged our black hole, but how do we extract this energy? Well, the answer involves a process known as superradiance, and it's as fascinating as it sounds. But that's a story for the next scene. For now, let's marvel at the potential of these celestial powerhouses turned cosmic batteries. To extract the energy, scientists propose a process known as superradiance. Now, you might be wondering, what exactly is this superradiance? Well, it's a phenomenon that's based on the theory that space-time itself is dragged around the rotation of a spinning black hole due to its intense gravitational field. Imagine gravitational or electromagnetic waves entering this region of rotation. These waves get pulled along in the dance of the spinning black hole. But here's the kicker. Assuming they have not yet passed the black hole's event horizon, the boundary beyond which nothing, not even light, can escape. Some waves might be deflected with more energy than they initially carried. That's right. This process involves converting the black hole's rotational energy into deflected waves. It's like getting a boost from the black hole's own spin. The more significant the black hole's mass, the more rotational energy it possesses, and the more energy can be extracted from the deflected waves. But how does this happen, you ask? Well, as these waves enter the region of rotation, they interact with the black hole's gravitational field. This interaction causes the waves to gain energy, a kind of gravitational slingshot effect. When the waves are deflected out of the black hole's vicinity, they carry away some of the black hole's rotational energy. This energy can, theoretically, be harnessed. So we've got a way to charge a black hole, and now we've got a way to extract energy from it too. And all this energy extraction is going on without crossing the event horizon, the point of no return. It's like we're siphoning off power from the edge of oblivion. But remember, this is all theoretical. Scientists are still working out the details and the practicalities of this fascinating concept. But it's an exciting thought, isn't it? That's one way to extract energy. But there's another method, and that's what we'll explore next. The second method involves extracting energy in the form of so-called Schwinger pairs. Schwinger pairs, you might ask? Let's delve into this fascinating concept. Named after the physicist Julian Schwinger, these pairs are a duo of particles that spontaneously pop into existence in the presence of a strong electric field. They consist of an electron and its antiparticle, a positron, which is essentially an electron with an opposite charge. Now let's bring back our fully charged black hole from the previous scenes. The electric field near the event horizon, the point of no return for anything that gets too close to a black hole, might be so powerful that it triggers the formation of these Schwinger pairs. It's like the universe's own magic trick, creating particles out of seemingly nothing. Here's where things get really interesting. If our black hole is positively charged, the positron from the Schwinger pair would be repelled by the black hole's electric field. This runaway positron, a particle with its own energy, could then theoretically be collected. Yes, that's right. Collected as a potential source of energy. It's a bit like catching a lightning bolt in a bottle, only on a cosmically grander scale. But before you start dreaming about black hole power plants, remember that this is still very much theoretical. The technology required to fully charge a black hole, let alone collect energy from runaway positrons, is far beyond our current capabilities. However, this doesn't dampen the excitement of scientists and science enthusiasts alike. The possibility of harnessing energy from one of the most powerful and mysterious entities in the universe is a testament to the limitless potential of human ingenuity and the never-ending quest for knowledge. Harnessing energy from black holes may still be in the realm of theory, but it's a fascinating concept.